Hey guys, welcome back to my channel. In today's video, we're gonna make an LED that actually breathes. Yeah, it's not blinking, it's fading in and out smoothly, just like it's alive. So, what's the goal today? I will show you how PWM works on STM32, how to figure it step by step, and how to use it control LED brightness, all the way from theory to real working circuit. And by the end, you will know how to control any output device, not just LED, but even motors and buzzer using the same concept. So before we jump into the LED part, let's talk about how we actually program the STM32. There are two main ways to write code into it. Number one, using Kill with the STM32 standard peripheral library or by accessing register directly. Number two, using STM32 Cubo IDE, which can auto-generate a lot of setup codes for you. Both are work. In my project, I'm using Q to implement it. Alright, so why do we even need PWM for this breathing light? If we just set a GPIO pin high and low, the LED either turns on and off. There's no in between, but we want it to fade. That's where PWM. It stands for pulse width modulation. PWM control how long a signal stays on within a fixed time period. The longer it's on, the brighter the LED appears to our eyes. So by changing that on time smoothly, we can make the LED fade in and out. That's the breathing effect. Let's take a look at how this actually works inside STM32. We have a timer, which is like the heart of PWM. It's made out of a few important registers. The first is a prescaler, the second is an auto reload register, and the third is a compare register. You can easily to understand these three of things by combining this figure. It's a general purpose timer block diagram. Normally, we just use the internal clock, and after that have a prescaler. It determines how fast the timer counts and divided the main clock frequency to generate the timer's internal clock. So it determines the speed of the counter. The second ARR, auto reload register, so it defines the total count for one complete PWM cycle. When the timer's count reaches the ARR, it reset. CCR defines the duration for which the PWM signal stays high within a single cycle. It controls the duty cycle. Here are three key equations that you will use when setting up the PWM. First is the PWM frequency, the second is the duty cycle, and the third is the resolution. So based on your project, you can design the frequency, duty cycle, and resolution you want, and determines the value of PSC, ARR, and CCR. Now let's take a look into the coding in the project. The main part in this project is the PWM initial function. Let's take a look into the definition. So in this project, we will use two peripheral, which is timer 2 and GPIO. So we need to enable the two peripheral clock of APB2 and APB1. The second part, we need to initiate the time-based unit. We use the internal clock to configure the timer 2 and set up the value of the ARR to 100 minus 1 and the value of the PSC to 720 minus 1. It means we set up the frequency of the PWM to 1 kHz. A third part, we initiate the output compare unit. We set up the OC mode to PWM1 and the polarity to high and enable the OC unit. And the pulse, it means the value of the CCR. We just set up to 90, it means 90% of the duty cycle. And we just initiate channel 1. Use channel 1 as our PWM output. Because of we using the timer 2 and the channel 1, we can take a look about the pinout diagram of the STM32. It means we need to initiate the GPIO to alternative function output. So the timer 2 channel 1 is PA0. So we need to set up the GPIOA pin 0 to the alternative function output mode. Yeah, this is the code. And the last thing, we just need to enable the timer 2. Here, we already finished initialize the PWM function. Next, we need to do just constantly changing the duty cycle of the LED to make the LED display a breathing effect. By using set compare function, we can just change the value of the CCR of the timer. This is the method we can just change the duty cycle of the LED with using two loops to increase the duty cycle of the GPIO from 1 to 100 and decrease from 100 to 0. So the LED will display a breathing effect. We just build it with 0 error and load it. This is how it displays. In the conclusion, we successfully implemented PWM to create a smooth breathing LED effect. We configure timer and GPIO pins for PWM output generation, and we developed a software loop to control LED brightness. Thank you for watching and see you in the next project video. Bye.